Okay, let me welcome him. Good evening, everyone. I have great pleasure in inviting you all to the first quantum talk of 2022, presented by Professor Marcel Mudrich from the Aarhus University, Denmark. So he's going to talk about the fascinating quantum fluid clusters based on helium nanodroplets for basic and applied research. In fact, this is the seventh in the series of Quantalks and the first in 2022. So welcome, Prof. Marcel. Now I request my colleague Siva to introduce the speaker.
Yes, indeed. Thank you, MSR, and I hope I'm audible fine.
Yeah.
So, yeah, it's indeed uh, uh, my extraordinary pleasure to introduce Marcel Modric, an associate professor at the Department of Physics and Astronomy in the Aarhus University in Denmark. So, indeed, this colloquium is very apt that Marcel presents it because he has been working in this field and is really an expert in many aspects of these quantum fluid clusters and very exotic cold quantum system. Marcel came here through a very fascinating, interesting journey. He did his PhD at the Max Planck Institute for Nuclear Physics in Heidelberg and graduated with the highest grades, which is summa cum laude. His PhD supervisor or advisor was Matthias Weidemuller. Even before that, he actually stepped into the physics of cold atoms, doing his diploma or master's thesis again at the MPIK, Max Planck Institute for Current Physics or Nuclear Physics, supervised by another very prominent name in this, Professor Rudi Grimm. Before that, he did his studies in the St. Petersburg University in Russia and also his undergraduate studies again in Heidelberg at the Heidelberg University. He held a postdoctoral position called the Elite Program for Postdoctorate and then transitioned into the University of Bielefeld in Germany after doing a postdoc at CNRS Orsay. And he then did his dissertation at the University of Freiburg, where he earned the title Privatdozent and was then an associated professor over there. He moved to sort of full academic position at Aarhus University in Denmark since 2017. Indeed, it's a pleasure to have Marcel, who's actually here in Chennai geographically at the moment. He is here on 3 accounts. Say, first, the team for promotion of academic research from the Ministry of Education or former Ministry of Human Resource Development, the Government of India, and a parallel program, the Danish International Network Program, supported by the Ministry of Higher Education in Denmark. So we are really fortunate to have him as also a visiting faculty in our department over the past 3 years, and he has collaborated with us and given a significant impetus to efforts to work in this particular science. Marcel is also an associate of our work group, the Prospective Center of Excellence, which we call QuCenDiEM, Quantum Center for Diamond and Emerging Materials. In this sense, it's only very apt that Marcel himself presents to us today this very unique quantum fluid system, helium nanodroplets, says are fascinating quantum fluid clusters, great potential, basic and applied research. Now the floor is yours, Marcel.
Okay, thank you, Shiva, for this great and very kind introduction and for hosting me here. It's the third time actually that I'm visiting IIT Madras, and it has always been very enjoyable. I hope our long-standing collaboration will continue. So I'm particularly grateful to the Spark program within which I am visiting now the second time already. And one student has visited my lab from IIT Madras on this program already, and second one will visit soon, hopefully, if the situation remains more or less stable. And yes, so let me start with the talk about helium nanodroplets. This is a topic that I have got fascinated with over the past 15 years now, where although my background is ultra-cold atoms and Bose-Einstein condensates, and there is some similarity between the two, but it's limited, as you will see in a minute. Maybe just one word to this title page here. What you can see, we will get back to that a little bit later, is two excited helium atom dynamically perturbing a superfluid, so an extended superfluid, and eventually merging and interacting with each other. And you will see in a minute what's happening when this occurs. So the menu of this colloquium here is, let me first introduce a few basic aspects of helium nanodroplets, in particular their peculiar quantum properties. Then I will present some examples of how you can actually image more or less directly single helium nanodroplets flying through free space, both pure and doped helium nanodroplets. And in the second part, then I will talk about dynamics of helium nanodroplets. How do these superfluid nanodroplets behave when they are being perturbed and respond to ultra-fast perturbations? This is ultra-fast spectroscopy. Then, before I forget this, let me thank the main actors that have contributed to this and many other topics of my work. So my group is a rather small group in Aarhus with two postdocs currently, Eltaif and Björn. Jakob is PhD student. Mykola is a former PhD student. René is a master student. And I forgot Agash Sundalalingam, who is a master student since since half a year now, almost. Another student will join. Other people to mention are Aaron LaForge at UConn in the US, and Shiva here from IIT Madras. I mentioned that we have been collaborating over many years now, and I will show a number of results that have been obtained during these collaborations. Also, Keshav Sishodia, PhD student, is involved. Sudha Sattva Mandal was involved in some of these experiments, and I'm collaborating with MPIK in Heidelberg, Paris, and the Fermi facility, Fermi at Electra, that's a free electron laser facility with the staff there, have been crucially contributing. My former group in Germany, headed by Frank Stinkemeyer, also contributed. So helium nanodroplets, what are these? Well, these are a very special type of rare gas clusters. I mean, any rare gas can be forced to condense into clusters. Helium, being the most inert material, is the hardest to condense into clusters, but you can. All you have to do is cool the gas to very low temperatures and expand it into a vacuum at high pressure, and then these clusters form, which eventually, however, are extremely weakly bound because helium is such an inert species. So the binding energy of the helium atoms to one another just amounts to about 7 Kelvin per helium atom. And in order for these clusters to actually remain bound and stable clusters, they have to be very cold. And this occurs by just spontaneous evaporation of helium atoms to then within a nanosecond or so reach a terminal temperature of 0.37 Kelvin. So this is very low, close to absolute temperature zero. which makes the helium droplets superfluid. How this superfluidity can actually be asserted, this is actually quite a matter of research that has been addressed by various means and is still actually ongoing research. One very interesting aspect of these helium nanodroplets is that they can be used as so-called nano-cryo-reactors. Yeah, they are very efficient in picking up foreign species, for example, other rare gas atoms like xenon or any type of molecule. Most of these foreign species then submerge into the droplets, and if several of these are doped into the same droplet, they would actually even aggregate and form an ultra-cold aggregate inside such a droplet. There are a few exceptions. Namely, the alkali metals have the property of only very weakly interacting with the helium, which makes them reside in these dimple states at the surface of the droplet. Yeah, so this gives a knob to control the position of where dopants are located, either inside or at the surface of a droplet, and we will come back to that in a minute. Yes, these helium nanodroplets are in a way an extreme heterogeneous system, because helium, as I mentioned, is very inert. It's transparent. It has an extremely high ionization energy, very high excitation energies, whereas compared to any other species. So this opens many opportunities to probe a system where really the chemical and physical properties of the host matrix, being the helium droplet, and whatever guest species inserted into the droplet are extremely different, such that solute-solvent effects can be probed very well. And in the spectroscopy field, these helium droplets are typically called ideal spectroscopic matrices, because due to their being so extremely inert, they perturb any molecule embedded in the droplets the least, such that infrared and also laser spectra of molecules in these helium droplets typically are extremely narrow, so highly resolved and very cold. So for spectroscopy, this helium droplet environment is very beneficial. Okay, how do we create these? I mentioned we just have to expand cold helium gas at high pressure into vacuum. And by cold, I mean around 10 Kelvin nozzle temperature. Under these conditions, in this adiabatic expansion, gaseous helium then condenses into these nanodroplets, into a beam of nanodroplets, which propagates. Of course, we need differential pumping to cope with the high gas load. These droplets then fly on, can be doped in the simplest case just by passing them through the vapor of whatever species we would like to dope them with, and then on into detector chambers where the actual laser probing or deposition on surfaces or other experiments then are performed on these doped helium droplets. Another interesting or practical aspect is that just by changing the temperature of the helium nozzle, the size of these droplets can be varied in a very wide range, from just small clusters containing hundreds of atoms up to micro droplets containing 1 billion or more helium atoms, and having then micrometer sizes, and that can be tuned just continuously. Yes, I mentioned that these are weakly bound systems and very cold, which makes them superfluid. So this entails a few interesting properties. Let me just mention two special types of dopants which would be a positive ion. Now, this is also ongoing research. What structures and what dynamics occurs when these droplets are doped with ions, and what actually happens, roughly speaking, is that an ion embedded in a helium droplet, due to the very strong electric field gradient around an ion, would polarize the surrounding helium, and by an effect like electrostriction, compress the surrounding helium to form a dense shell of helium, which can actually, where the density can actually surpass the density of solid helium. And these kind of structures would then be called snowballs. On the other side, a negative ion, or just an electron, has the property of repelling helium. That can be easily understood from the fact that helium atoms have the ideal rare gas configuration, electronic configuration, and don't want any electrons nearby. So by Pauli exclusion principle, surrounding helium atoms surrounding an electron would be repelled, and a bubble forms. This has also been studied theoretically already a long time ago. And these electron bubbles in superfluid helium, due to the large volume of about 3.4 nanometer diameter that they create, tend to be actually repelled out of the superfluid towards the surface, and eventually detach even from the surface. A very famous experiment to probe the superfluid properties of helium droplets was performed by already 20 years ago now by Andrei Vilesov and Jan-Peter Tönjes, spectroscopically. Yeah, of course, probing superfluidity like in bulk superfluid helium by moving objects around or so is not feasible for these nanometer-sized droplets. But in analogy to the Andronikashvili experiment, this rotating disk experiment in bulk superfluid helium, in analogy to this, molecules were embedded in helium droplets and were excited into rotational states. And this rotationally resolved infrared spectrum was recorded for OCS molecules embedded in a pure helium-4 nanodroplet. So helium-4 is the most abundant species of helium, and that's the substance that is superfluid. And what you can see is that the rotational lines in this infrared spectrum are very sharp and narrow and well resolved, and spaced by almost the spacing that you would expect for a free rotor in free space, telling us that indeed it seems like a molecule in such a helium droplet undergoes quasi-free rotation, which we would expect for a perfect superfluid. And the smoking gun for demonstrating the superfluidity of the helium-4 droplets was this direct comparison with helium-3 droplets. Helium-3 is the fermionic isotope of helium, which also can be made to condense in droplets. However, these droplets, which have more or less the same temperature as, or even slightly lower temperature compared to the helium-4, do not undergo this phase transition to the superfluid phase, because they are fermionic species. And indeed, there's a similar experiment for these fermionic droplets showed only a very broad structureless feature, telling us that the rotational states are strongly perturbed, have short lifetimes, which we would exactly expect for a damped rotational motion for a non-superfluid. So this direct comparison was taken, or is still taken, as the most direct evidence for the superfluid properties of these nano droplets. Yeah, so that's frictionless, and here it seems to be a normal fluid. However, this the striking explanation was or is being challenged in a way when the rotational motion of molecules inside the droplets is excited not by a continuous laser, but by short pulses, which nowadays can be done in many laboratories. And in this experiment, which was actually performed in Aarhus by my colleague Henrik Stapelfeld and co-workers, this methyl iodide molecule was aligned by a kick pulse of rather long first pulse to adiabatically, impulsively align the molecule, and then the rotational dynamics of this molecule was probed by a second ultra short pulse, which then Coulomb exploded the molecule, and by detecting the direction under which the fragment ions are emitted, the orientation of the molecule can be probed as a function of the delay between the two pulses. And in that experiment, which Henrik Stapelfeld routinely does for free molecules, you would expect these revival features of the molecule being impulsively aligned. Then by dephasing, the alignment is dephases until all the rotational states come in phase again. This is the so-called rotational revival, and this repeats in the delay time, showing that the rotational motion of this molecule remains coherent over a long period of time in free space. If we compare this to the molecule embedded in a helium droplet, then we see that this alignment signature is fast, but then the loss of, so the dephasing or the loss of rotational of orientation is significantly delayed by tens of picoseconds, and it never comes back. Yeah, so they don't see any rotational revival, and that is, in a way, it seemed to be in contradiction at that time to the concept of droplets being perfectly superfluid and allowing the molecule to freely rotate. But it turns out that in such an impulsive scheme of exciting rotation, the surrounding the shell of helium around a molecule actually lose their superfluid properties. They have to be treated more classically, like really a shell of classical atoms around the molecule, and would then perturb rotation. By now, they have repeated this experiment for many different types of molecules, and in particular for impulsive and also adiabatic alignment. Adiabatic means that the alignment pulse is much longer, and actually it is they found interpretations to reconciliate with the CW experiments. But what remains is an impulsive motion is clearly perturbed by the helium droplets. And just to highlight a recent result from that group, where such a diiodophenyl molecule, I think it was again adiabatically aligned in this case. So here they used the gray shaded area indicates that the alignment pulse. This was quite a long alignment pulse to let's slowly align the molecule. And then, so the right-hand side is just a close-up of the falling edge on the left-hand side. Then by comparing the gas phase, which is the black line, where then the alignment is again lost after about 20 picoseconds. In helium droplets, this aligned state of the molecule survives for much longer time, up to almost 50 picoseconds. So this shows that even for an adiabatically aligned larger molecule, the loss of rotational alignment is slowed down, and this actually could be a very interesting effect, in particular in the context of these new experiments that are becoming possible at free electron lasers, where the goal is to directly image by X-ray diffraction, image individual molecules. There, of course, it would be very beneficial to be able to prepare a molecule in an aligned or even an oriented state of the molecule, to then take a snapshot of the molecule with the best possible control. And since now this alignment and orientation of molecules is a tough business, doing this in droplets and basically freezing the state of alignment for a certain time, where then the laser pulse is gone, and we keep the molecule in this aligned state in free space with no laser around. This would be very beneficial for these X-ray diffraction images. And that's actually the next topic that I would want to come to, just to visualize this vision that was actually announced more than 20 years ago now, that it should be possible by using ultra short X-ray pulses to actually diffract an X-ray pulse from ideally a relevant biomolecule in free space, record the diffracted photons from this one molecule in a single shot experiment on a scattering detector, or even two scattering detectors at wide angle and small angle, and then retrieve the full structure information of such a molecule, ideally with atomic resolution. So this still remains a vision. I mean, diffraction imaging is possible. You will see this in a minute. Atomic resolution cannot be achieved to date with the wavelengths that are available at these laser sources today. But immense progress has been made over the past 20 years, and this is a development that is moving on very fast. So the first facility that provided ultra short, not X-ray, but XUV and soft X-ray pulses was the free electron laser at Hamburg, FLASH, which is this facility here. And now there's actually a FLASH 2, there's an upgraded version. Soon after, the first X-ray FEL came online. That's the LCLS facility in Stanford. There's another very nice XFEL in Sakla in Japan. I will actually also address a soft X-ray laser Fermi in Trieste, which is actually the first and so far only seeded free electron X-ray free electron laser, and the most powerful free electron laser, that's the European XVL in Hamburg, which has a total length of 3.5 kilometers, reaching all the way from the city of Hamburg to the federal state of Schleswig-Holstein. So, okay, federal states in Germany are a little bit smaller than in India, but still, this is always, this may be very impressive. So I mentioned that molecules eventually should be imaged to ideally biomolecules to find new drugs or resolve fully the structure of COVID viruses or so. This, of course, can also be done with other very interesting types of systems, for example, helium nanodroplets. And actually, 6 years ago or 7 years ago, Andrei Vilesov and co-workers have undertaken this experiment at LCLS, where they produced a beam of helium droplets, quite large ones, up to micrometer size, either pure or also doped ones with xenon atoms, and recorded these single-shot X-ray images. And what they saw is a variety of different shapes of these scattering images, out of which they could then reconstruct with some sophisticated methods the actual shape of the droplets in real space. So most of these droplets are actually spherical, but some are have this ellipsoidal shape. They have actually found oblate and also prolate droplets. And but overall, the shapes of these droplets did not show very surprising features compared to classical liquids. So it seems that the shapes of superfluids are follow pretty much also that what you would expect for a classical liquid. However, there is a peculiarity about superfluids, namely that they theoretically are irrotational. Yeah, they cannot sustain rotational flow in a superfluid. So if a nanodroplet is forced to rotate, for example, in the experiment, this happens naturally when this helium droplet pops out of the nozzle and kind of sticks to the wall, then it tends to get some angular momentum transferred. Then this angular momentum distributes into so-called quantum vortices. And these quantum vortices have been measured in bulk superfluid helium a long time ago. But here, really for the first time, it was possible to take snapshots of helium droplets containing these vortices on individual helium droplets. And the way they observed them is, first of all, they had to dope the droplets with xenon atoms, where the xenon atoms actually are attracted into the vortex cores. And since xenon are electron-rich atoms, they scatter X-ray light much more efficiently. So they actually acted as contrast agent. And then what was then visible in the diffraction images is this periodic pattern here. And the periodic pattern in reciprocal space means that there is also a periodic pattern in real space, which is this arrangement of this periodic lattice type structure of vortices, very much resembling these vortices that were previously, like 50 years ago, measured in bulk superfluid helium in this famous rotating bucket experiment, using electrons to visualize the structure of these vortices. And actually also in more modern times with Bose-Einstein condensates, which were stirred by laser beams, these regular vortex structures were observed. So this all makes sense and is another direct manifestation of superfluidity of these helium droplets. And in more recent experiments at even higher photon energies, shorter wavelength, to get even better spatial resolution. I mean, this is fantastic that actually the shape of these vortex lines could be made visible on a spatial resolution of better than 10 nanometers scale. So this is, I find, really amazing what level of degree it's possible to extract out of these diffraction images for individual nanoparticles. Yes, that's the aspect of imaging pure and doped helium nanodroplets. So actually, I am very much fascinated by this method, and not only me, Shiva Ramakrishnan also is. So we thought, why should we not apply for a beam time and do such an experiment ourselves? Actually, This flash laser in Hamburg is not so far away from University of Aarhus. For Shiva, it was a longer journey, but he made it last year. And by using such an arrangement of a pulsed helium source, creating a beam of helium droplets, which is then intercepted by a soft X-ray laser beam, we actually were able to record similar diffraction images. However, we went even one step further and added another laser beam, an intense infrared laser beam, to excite or even highly ionize the helium droplets, and then in a pump probe scheme try to detect the dynamics of these excited helium droplets on an ultra short time scale. And this is ongoing work. Keshav, Shiva's PhD student, is now digging his way through all these many images that we have recorded. One typical one for just a pure droplet imaged by one soft X-ray pulse is this. So we again see very regular fringes telling us that this is a round helium droplet. For xenon doped droplets, where we also recorded images, there's a variety of patterns, but some show similar fringes as the pure ones, but you can maybe see that there is some some interference pattern on top of the round fringes. And we also did helium droplets doped with alkalis, with potassium atoms. I mentioned that these are special species which attach to the surface, and there indeed the diffraction images look completely different. We see this pronounced streak features here, which we are currently trying to analyze and understand better. And a first glimpse into this ongoing work is shown, you can get here. That this is done by a student of mine right now, who tries by forward simulating these diffraction images using intelligently guessed initial structures. For example, a helium droplet with two scattering centers inside the droplet was actually able to reproduce this additional interference pattern on top of the fringes, which resembles the measured ones. So in this way, we are trying to understand better what's going on. And this is already in a way of a surprise, because until now, the concept was always that due to the superfluid properties of the droplets, any dopants would swim around freely in the droplet and aggregate into one single center, into one cluster in the center of the droplet. But it seems that for large enough droplets, actually multi-center aggregation can occur, which we seem to actually have evidence for here. These guys, these surface doped droplets with potassium, might actually, also these streaks might actually indicate this surface doping. So another colleague who has performed similar experiments has evidence, or has done some simulations also, where he found out that if there is one dimple, or actually many dimples, then the diffraction images tend to show these spider-like patterns with extended streaks, and that could be an indication for that these potassium clusters are actually formed on the surface and not inside the droplet. What about the pump probe? So we actually I mentioned we had a second strong near-infrared laser pulse. where we thought that we would be able to see some pump probe dynamics, for example, the explosion of a droplet on the time scale of, typically this happens within few picoseconds, because I mean, Coulomb interaction of ionized helium atoms is very strong. Helium is very light. So we know from previous experiments that at least small droplets would explode just within a few picoseconds. But what we found here for these large droplets is that we have to wait for hundreds of picoseconds or even a nanosecond until we actually see fragmentation of the droplets, and the fringe pattern then completely disappears, and we see this very chaotic speckle-like pattern, which, by comparing to other cluster systems that have been studied, seem to actually indicate that such a droplet then fragments into a large set of probably neutral residuals, which then create such a speckle-like pattern, but this is still ongoing analysis. I have to mention that similar experiments have been also done recently at the European XFEL, which is a hard X-ray machine by another collaboration where also different species were doped into the droplets. And actually, for different atomic dopants and different molecular dopants, they actually found very characteristic differences, clearly showing that the different types of materials aggregating in these helium droplets form very different types of aggregates, probably either compact single or multiple sites, like I just also mentioned with what our observation with the xenon clusters. But also it seems like more open structures or even foam-like structures can form in this unconventional ultra-cold helium environment. Yeah, so this aspect of aggregating unconventional materials in helium droplets is an interesting one, maybe actually for applications to form novel types of materials, which eventually would have to be deposited on a surface to bring it out of ultra high vacuum and these special helium droplets into the real world. And there are a few groups who actually work on it. And one prominent example is shown here, where using large droplets that were first doped with silver and then gold, these researchers were able to form core shell bimetallic clusters and deposit them on a microscope grid. And then depending on the size and the conditions of the droplets, either these type of nanowires, or even, so this I think is a microgram of metal, and a metal nanowire, but also silicon nanowires were formed, or this core shell silver gold nanostructure was formed, where depending on the order of the doping, first silver and then gold, or the other way around, they were actually able to control the structure of this core shell particle, either silver inside and gold outside, or the other way around. And another interesting aspect of these nano droplets, or the method of depositing aggregates on a surface, is that you can see here in the upper right corner, this is a simulation, density functional theory simulation of the deposition process of a dopant on a surface, where you can see that such a superfluid helium droplet actually shows all sorts of interesting interference effects. It is a quantum fluid. But more importantly here is that due to its low temperature and this highly dissipative character of these droplets, one may expect that such an aggregate is deposited in a very gentle, soft landing condition, such that possibly even very fragile complexes aggregated in a droplet would be gently deposited on a surface without without changing structure so much. I just wanted to mention that actually just a few weeks ago, another group published result where using helium droplets, bismuth clusters were deposited. And they were specifically addressing this aspect of soft landing deposition. What happens to these, or how efficient is the deposition of these aggregates at all? And surprisingly, what they found is that in this deposition process, actually, many of these aggregates in the droplets do not directly stick on the surface, but actually rebound from the surface. And some of them were actually collected on this grid number 2, standing perpendicular to the beam direction. That's this microgram on that side, showing that, and they also spectroscopically showed that quite a number of these aggregates do not directly deposit on the surface, but actually are backscattered by the splashing effect of these helium droplets. And this may be bad news for efficient structuring of surfaces, but it might be also good news in the sense that what they observed for charged aggregates, that this is actually a very efficient way to extract these charged aggregates out of the droplets with a variable number of helium atoms attached to them that can be used actually as tagging agents for helium tagging spectroscopy, which is a very nice spectroscopic method. It's an type of action spectroscopy where that's background free, and that allows to do high resolution spectroscopy of ions with very high sensitivity. Good, that's the aspect of imaging and actually even depositing aggregates. Let me come to the last part where we did experiments on probing the dynamics of these helium nanodroplets. And these experiments were mostly done at another free electron laser. I mentioned the first seeded free electron laser Fermi. That's this linear accelerator structure here at the Elettra facility in Trieste in Italy. And we were using the low density matter beamline in the experimental hall over here, and used helium droplets. And to get started with studying the dynamic response of helium droplets, we were interested in seeing what happens when we at all just resonantly excite a helium droplet. Or probably what happens is that we excite one helium atom in a droplet, and then probe the dynamic response of such a helium droplet by sending in a second pulse and recording electrons in this case. So the scheme that we chose is let's excite into this strongest absorption band, which is the black profile shown in upwards here. So the energy scale goes up. That's the excited states correlating to the strongest absorption state 1s2p of helium atoms. And then with a probe pulse, we ionize this excited state and detect the photoelectrons that are emitted, which should tell us about the energetics of the excited states as a function of time. And this is the electron spectra, now plotted in vertical direction as a function of the pump probe delay. So first surprise was that at around 0 delay, where we would expect really a direct 1+1 photoionization event to happen, basically we would expect that the electron energy is just the excess energy from absorbing 2 photons that is depicted as this dashed line up here. We do not observe any electrons up here. So what happens, it seems, is that when we excite a helium droplet, then within the pulse duration of that scheme, which was 100 femtoseconds, we have very fast energy relaxation by about 1 electron volt, and then down relaxed state is populated. And then after about half a picosecond or so, there's another transition, it seems, into the final excited state, which actually very well matches the atomic 1s2s excited state. So we have very fast electronic relaxation out of this 1s2p into the 1s2s droplet band, and then after some half picosecond transition into the unperturbed atomic excited state. So how can this happen? Well, the fast relaxation from the P into the S state, this most likely occurs along these level crossings that are already present in the diatomic potential curves. But then we are still in a droplet excited state. So how can it come about that we detect the unperturbed atomic excited state? And the answer to that was given by these time-dependent density functional theory simulations performed by Manuel Barranco and colleagues in Spain. And if I can run this simulation, then you see after excitation, this excited helium atom, because it behaves more like an electron, pushes away the surrounding helium, forms a void cavity, and then slowly moves to the surface and eventually is actually expelled out of the surface. And so that explains why an initially excited droplet then transforms into a localized excited atomic state because of this very fast decoupling of the excitation from the surrounding helium. Yeah, so this occurs according to this. So the opening of this bubble around the excited state, that occurs within a picosecond or so, and then on a time scale of 10 picoseconds or so, this bubble then moves to the surface. We actually recently did a similar experiment where we excited not into the lower excited band, but into this higher excited state here. And this higher excited state here is different in the sense that when we excite up here, then the droplets can already auto-ionize. So they're not just excited and relax and eventually decay by fluorescence, but even auto-ionization can occur. The resulting electron spectra are shown here. So only in the pulse overlap region, we see the direct 1+1 photoionization signal out of the initially excited band, but then again within a picosecond or so, the system very efficiently relaxes back down into the atomic, mostly the atomic 1s state. That's this peak here. But what is different is that we also see a triplet atomic state, which we would not expect to optically excite due to selection rules. But what happens here is that when we excite into this higher lying state, I mentioned that the system can auto-ionize to form a helium dimer ion and an electron, which inside the droplet can actually recombine, and in the recombination process populate this triplet state. Yeah, so it's auto-ionization recombination, and in this way we end up in this metastable triplet state, which we also detect. Let me mention, so this is the dynamics of pure helium droplets. Of course, it's also interesting to study atoms and molecules and other nanosystems that are embedded inside the droplets by femtosecond pump probe spectroscopy. And one nice experiment by another group working in this field was performed using indium atoms that are embedded in the droplets. But actually the dynamics is very similar in the sense that when this indium atom is resonantly excited, again, this excited state, this excited electronic orbital behaves more like a free electron, pushes away the surrounding helium, forms a bubble, and these excited indium atoms, if they are located towards the surface, that's shown in this bottom graph, they actually even tend to be again be pushed out to the surface and to be expelled. In a more recent experiment, that same group repeated that measurement, but for indium dimers, so simple diatomic molecules, which can be excited into vibrational states, and then probed. Then the vibration can be probed in time, which typically shows this. Can be shown as this oscillations in the photoelectron yield and also the photoelectron energy as a function of pump probe delay. And what they found is that actually there is damping or energy relaxation by coupling to the helium droplet, but after an initial energy flow into the droplet within 1 or 2 picoseconds, it seems this vibrating molecule forms the bubble, decouples from the surrounding helium, and this vibrational coherence was detected up to hundreds of picoseconds. So again, this shows that on a very short time scale, after perturbing the helium, it seems superfluidity breaks down, because it's like you give a kick to the droplet or to the helium. In that short moment, superfluidity breaks down. But once the system equilibrates more or less, then it actually starts to be very weakly perturbing, and then both free rotation and, in this case, free vibration of a molecule is possible inside this helium droplet. Just to mention that, of course, these kind of, and this is very fundamental physics, but people are discussing and actually tackling experiments where maybe more relevant systems are used and embedded in helium droplets. For example, I just made up this cartoon where some aromatic molecule and a C60 buckyball molecule are combined to form such an aggregate inside the droplet. I mean, these type of systems of these organic light absorbing molecules coupled to C60 molecules or complexes are actually very efficient complexes for light harvesting, as elementary units in organic photovoltaic devices, where in this case the helium droplets could possibly be used as very controlled nano laboratories, low temperature, high resolution spectroscopy, or for probing the charge transfer dynamics in such a system, for example, or maybe photocatalysis systems on a molecular level, where the helium droplet would act as a nano reactor to form these systems in a very controlled way. Okay, I just want to mention that back to our experiment where we resonantly excited the droplets with these free electron laser XUV pulses. Of course, using a free electron laser, it was an easy thing to multiply excite the droplets, and instead of just having one excited helium, have 2 or 3 or even more. And what then happens if we excite a pair of helium atoms is that these excited atoms can actually interact with one another. In particular, since these 2 excited atoms are embedded in a superfluid, so they are moving freely and can interact with each other very easily and exchange energy, where then one of the 2 can de-excite into the ground state, transfer its energy to the neighboring one, where then basically the one de-excites, transfers the energy, the other one is then ionized in this process. And this type of process is called interatomic Coulombic decay and has been studied by theoretical groups also very intensely over the past 10 years or so. And we actually see clear indications for this ICD, interatomic Coulombic decay process, to happen. For example, in the electron spectrum, we see a very clear sharp peak, which exactly matches the energy we would expect for this ionization process to happen. This, by the way, is a synchrotron measurement. So even at synchrotron conditions, so low intensities, we can observe these multiply excited droplets. But we were interested in seeing, is it possible to probe the dynamics? How fast does this ICD process happen? And so again, we applied a pump probe scheme by sending a second pulse that ionizes, and so ionizes the excited state population, and in this way depletes the excited state population, and in this way quenches the ICD process. And what we observed here, so down on the bottom panel, again, you can see this the photoelectron spectra, which show the relaxation dynamics and the low energy range. In the upper energy range, this 16 eV band, that is exactly characteristic for the ICD, for this energy transfer process. And indeed, what we see is that at short delay, or we can also integrate these signals, and so then the blue data points, that's the ICD signal. And we see that indeed at short delays, by ionizing the excited state population, we deplete the population and quench ICD. It shows a minimum. Of course, we quench it by photoionizing, so the photo electrons have a maximum accordingly. And then by the recovery time of this ICD signal, we get information about how fast ICD happens, because we get the minimum when we photoionize before ICD happens, but when ICD happens before photoionization, then we do see the ICD signal. So from the rise time of this signal, we can deduce how fast ICD actually occurs. And we did that for various excitation probabilities, so photon fluxes and droplet sizes and so on. The bottom line is that we end up with an always rather constant and rather short ICD time constant of less than a picosecond, and by half a picosecond to 1 picosecond. So by comparing with theory results, these were done by Nicolas Sissoura in Paris, from theory, and by assuming by plugging in the average distance between between the two excited atoms in such a pair of interacting excited helium atoms, we would actually expect quite a much longer ICD time, more in the range of 10 to 100 picoseconds. So there must be some mechanism that somehow speeds up ICD happening inside a helium droplet. And now we come back to this initial figure here, showing what happens when two excited helium atoms inside the superfluid are excited at time equals 0. And we know already every excitation forms a bubble. If these two bubbles are close enough to one another, the bubbles which actually merge, let me run it again, the bubbles merge, and by merging, the two excited atoms inside are pushed towards each other and basically collide with each other. And this, of course, speeds up the ICD process a lot. Okay, I mean, this, you may wonder, okay, this is nice, but it happens, of course, only for these nearby pairs of atoms. That's true. Of course, in a droplet at low intensity, we would probably excite two atoms that are much further away. In that case, they would probably just never meet, because these bubbles tend to then push them out of the droplet and they never meet. So this bubble merging effect on the one hand accelerates the nearby pairs, but on the other hand separates those pairs that are far away. And in this way, we just select out those active pairs that can undergo ICD very quickly. So that's the reason why we detect it very fast. Just to mention that this ICD process, I mean, seems very like maybe very of academic interest, but it turns out that actually in many natural systems, for example, a biomolecule that is microsolvated by a water molecule or a whole shell of water, and if that such a system is ionized, for example, inner shell ionized by an X-ray pulse, where the water is inner shell ionized, then this ICD process, so this energy transfer towards the biomolecule, can be actually very efficient, and cause damage to the biomolecule. And so mostly theory work have shown that this kind of energy transfer processes of biosystems exposed to ionizing radiation or to electrons actually are very much affected by these energy and also charge transfer processes. So at least we find it interesting to study these processes on a very fundamental level, where the helium nanodroplets help to decipher these very fundamental processes, which of course then which may be relevant also for more biological systems. So that's, I mean, it is known that in these biological systems interacting with ionizing radiation, actually most of the damage is caused by exactly these indirect secondary processes, and whereas the direct DNA damage from X-ray radiation is a minor channel. Most of the damage happens through slow electrons and through these energy and charge transfer processes. All right, just as a final word, and because it's so beautiful to see what you can do with free electron lasers and strong laser pulses, what we did in one more experiment on the same system, we resonantly excite the helium droplets, but then crank up the intensity of the second probe pulse, such that even several photons were absorbed by the same system. And in that case, the electron spectra look a little bit more complicated, in the sense that, again, down at low energies, we see this relaxation dynamics, but in addition, we see replica of these electron energy features here at multiples of the probe photon energy. And that's this effect is called above threshold ionization, because this one electron absorbs more than one photon that's needed to take it above the ionization threshold, and so it is promoted even further up into the continuum. And it seems, and this process typically needs very high intensities to be efficient. What we found is for helium droplets, this ATI effect is strongly enhanced. Yeah, so here you can see these electron spectra now plotted in horizontal direction, just for different droplet sizes compared to the black, which is just helium atoms. So under these intensity conditions, the atomic ATI spectrum very quickly drops off for the higher components of the electrons. Whereas when we increase the size of the droplets, you see that the high order ATI spectral lines become visible, and the electron energies extended up to tens or even up to 100 electron volts, just by going from atoms to helium droplets. And that is very surprising. And resembles in a way what we found in the literature. It resembles the effect of ATI in buckyballs in C60 molecules, where the electrons are highly delocalized across this scaffold of this carbon atoms. So actually, this concept of the superatom was coined in this context, and there also, due to this collective coupling of all these electrons, they found extended ATI features. So what we think might happen is that multiply excited helium droplets, all these excited electrons and the excited atoms interact, they couple together and cooperatively emit more energetic electrons from the probe pulse then. And yeah, this is still something to figure out in more detail, but a very interesting collective effect here. And as a last word, of course, we can even more highly excite the droplets. So not just 2 or 3 or 4, but almost all the helium atoms in a droplet can be resonantly excited if the FEL, the excitation pulse, is intense enough. And what then happens is that all these excitations very rapidly exchange energy and undergo what we call collective autoionization. So the whole system autoionizes, and this we can see by this ICD feature in the electron spectrum. From pairwise interaction, then broadens, shifts towards lower energies. This is because very rapidly this cluster evolves into a nanoplasma state, which has a strong binding attractive potential for electrons, which retains the electrons and thereby shifts down their kinetic energies. And characteristically, we see a strong then component of low energy electrons growing in, which are electrons emitted in a just thermal emission process out of this nanoplasma state. And this we have studied in this resonant excitation scheme, but I have to mention that renowned experts have done similar experiments already much earlier on helium nanodroplets, which were multiply ionized just by intense strong field near-infrared laser pulses, where then the final state actually is very similar, where the helium droplets is completely transformed into a nanoplasma state, which then Coulomb explodes and emits energetic ions and these thermal electrons. And this is actually still ongoing research with Shiva and me, and we have a joint project also to continue this work. That's it. I hope that I showed you some interesting aspects about the fundamental properties of helium droplets that you can nowadays directly or more or less directly image single droplets, pure or doped ones, by this X-ray diffraction imaging method. I showed you some interesting aspects of the dynamics of these helium droplets, and this is still ongoing work also. So with that, I thank you for your attention, and I will close the talk.
Thank you, Marcel, for this very fascinating talk. You really walked us all the way through from what these droplets are and gave directions for current, ongoing, and even future research prospects. The floor is now open for questions. So please either raise your hand or type it in the chat box, or perhaps just unmute and ask questions. There's a question from my colleague, Arvind.
Hi,
Arvind,
sure,
please
thank
go
you.
ahead. Hi.
Yeah.
Yes.
Hi. Nice, very
Hi,
nice
Arvind.
talk, Marcel. Very nice talk.
Thank
I
you.
just have one. I didn't understand a point about this helium bubble merging. Could you please explain that again? That you had low intensity with synchrotron, you have helium bubble merging. So that particular part, yeah.
Yes. Okay. Yeah, maybe. So I mean, this simulation. So this is a simulation that illustrates the merging. This is a simulation that goes along with the free electron laser experiments, where we had an ultra short laser pulse that resonantly excites a pair of helium atoms in a droplet, and where we then probed the dynamics by this depletion method, by sending in a second probe pulse that ionizes the excited state population. We probed the ICD yield as a function of pump probe delay time. Maybe what is that more or less clear?
No, that is my question is, you have at low intensities, so you have two helium, a pair of helium, which is not very close by, but they are somehow coming close by. They merge together. So what is the force that brings them together?
Yeah. Okay. I mean, that's a very good question, because I mean, I mentioned that in the when I introduced this spectrum here. This was actually measured at the synchrotron, where the intensity is orders of magnitude lower than in this free electron laser experiment, and still using very large droplets. We measure this feature, which in that case most likely comes from, as you say, a pair of excited atoms that are very far away from each other, which both are form bubbles, are expelled towards the surface, but still remain attached to the droplet surface, swim around or move around the surface, and eventually meet each other, and then interact and decay. And the reason why they would meet each other is because the polarizability of helium atoms in the excited states is orders of magnitude larger than the polarizability in the ground state. So just by induced, I guess it's induced dipole-dipole interaction, they would, since they are both highly polarizable and highly mobile on the droplet, they would approach each other and then decay.
Okay, and they before their lifetime they have to come close by.
Yes, and I mean they are in both these singlet and triplet S states are metastable, so they have enough time to do that.
Okay, thank you very much.
Yes, very welcome.
Yeah, thank you for the nice question, Professor Sethupathi. Yes, please go ahead.
Yeah, Marcel, that's a very good the presentation. I just have some nail questions. This is regarding the typical size of these nano droplets. What is the typical size?
I mean, it can vary a lot. I mentioned that in the beginning, that just by changing the experimental parameters, we can vary the size from less than a nanometer up to more than 1,000 nanometer. So so that really that of course greatly changes the properties, and in particular the surface to bulk ratio changes a lot. And then it depends what application do you want the droplets for. Typically for spectroscopy of individual molecules embedded in just one droplet, we would use small droplets, because it doesn't help to have a very big shell around. We just want a molecule just embedded in a droplet to be cooled down to low temperature and to be dragged along in the beam. And then it's better to have smaller ones, but more of them, to get a higher, stronger spectroscopic signal. However, if we are interested in forming these nano aggregates, like these core shell metal nanoparticles, or even nano wires or other complex structures, then the droplets have to be much larger to supply enough cooling capacity to actually cool down and aggregate these large structures. So in that case, we would typically use droplets that are hundreds of nanometers large.
Do you have a control over the size of the droplets?
Yes, just by changing the experimental parameters. So just by, mostly it's just tuning. I mean, when we have this nozzle expansion out of the cryogenic nozzle, it's just about changing the temperature of the nozzle.
I see. So
if we approach the boiling point of helium under these pressure conditions, eventually we would even create a liquid beam of a liquid jet of helium. That is very hard to control. So, but just above the boiling point, we would generate very large droplets in the micrometer.
I'm sorry, this is all in the vacuum environment.
This is all in vacuum, yes, of course.
So you maintain the pressure of 50, because I heard you were saying about the superfluid helium.
Yes.
So I thought maybe superfluid is around 300 millikelvin, 370 or so millikelvin, and you said high pressure also. So
yes.
How do you maintain that?
That maintains spontaneously I mean, once the droplets form and just travel inside the vacuum, they do not interact with anything around them because they are completely transparent. Also, they are transparent to black body radiation. They ideally do not collide with any residual gas. So they spontaneously cool down to this 0.37 Kelvin just by plain evaporation of helium atoms. Just given this temperature is given by basically by the binding energy of the helium atoms. That's similar to atoms in a trap. If the trap depth is a millikelvin, then the trapped ensemble will thermalize to roughly a tenth of that. And that in this case, the trap depth is given by the binding energy of the helium atoms, which is around 10 Kelvin or 7 Kelvin. So the terminal temperature when plane evaporation stops is around a tenth of that, so which is then 0.4 Kelvin. And whenever we perturb the droplet by, for example, doping a molecule, which of course inserts a lot of energy, because the molecule typically is at room temperature, has many degrees of freedom and so on, then the molecule again is cooled down to this droplet temperature very efficiently at the expense of boiling off helium from the surface of the droplets. So the droplet would shrink. So the droplet has to be large enough in the first place to supply enough cooling capacity by evaporation.
Thank you. Thank you.
Yeah, thank you.
Yeah, please go ahead, Prof. Venki.
Yeah, you know, what's very interesting is recently I heard some talks on you know, laser fusion, you know, at places like Los Alamos and Lawrence Livermore, where they essentially they put these various deuterium and tritium and all these atoms a small gold bubble kind of thing. And then they bring lasers from different directions and compress the whole thing to very high pressures. I'm just wondering whether this technique of creating this helium bubble and trapping atoms inside may give another approach to kind of laser fusion kind of thing. Have you thought about that?
Yes, well, no, not not any well-founded thoughts, but I mean, I think of course these micro pellets or these targets that are used for laser fusion are much larger, and the mechanism is that the material is compressed by inertial confinement. It's compressed together, so I mean that requires, I mean, definitely micrometer-sized these targets. So with the helium droplets, we are probably an order of magnitude or so smaller than that. I mean, I think the structure of these targets is very important. So it has to be, they have to be designed very specifically. I'm not sure if a large helium droplet would be the best medium to form such a designed target in the first place. Yes, so I'm not sure. I mean, I haven't looked much into this inertial fusion business yet, but my feeling is that they are dealing with larger targets, and that need to be very specifically engineered. Maybe which way you need really more degrees of freedom than what such a helium droplet would offer you. Yeah. I mean, maybe to mention one more word to that treats deuterium clusters. So large deuterium clusters have been used for nuclear fusion experiments that were induced by very strong infrared laser pulses. So it is possible to ignite nuclear fusion in deuterium clusters. However, the mechanism is different. I mean, this is really a nanoplasma. It's a laser-driven plasma that is excited to very high temperatures and high densities, Whereas in this inertial fusion, this is more a compression effect, where so it's a different mechanism.
Hi, Marcel.
Yes.
You're done, Venki? Nice cap anyway.
Yes.
So, a very interesting talk, Marcel. I have a couple of questions. So these vortices, the quantum vortices.
Yes.
So they're not spherical in shape. Is it because the droplets are rotating?
Ah, that's a good question. I mean, I think one reason is that I'm not an expert in that, but as far as I know, these vortices, when they end up on the surface of a superfluid, they tend to stand perpendicular always. So that already makes them not all being parallel, because they have to end up perpendicular on the surface. But I mean, why they have these non-linear shapes, these quark polar shapes? I cannot tell you in detail. It's maybe it's actually due to the fact that the droplets are not perfectly spherical, and they of course, these droplets have also all sorts of surface modes that can be excited, and these large droplets. So there's different elementary excitations like phonon modes, what is called riplon modes, which are surface excitations, and then these vortices, which probably couple to one another, but I'm not sure if it's fully understood what makes these shapes of the vortex lines.
And then probably the density of these vortices are also dependent on the size of these droplets, I suppose. Suppose in bigger size droplets, the density of these vortices will be the same in all. If the droplet size is bigger, for example.
Yeah, I mean, again, I'm not an expert, but as far as I know, the vortices interact with each other. That's what causes them to arrange themselves in this regular pattern. So I think compressing the vortices more is hard because of this repulsive interaction. Getting them more dilute is probably possible, but it's, from what I've seen, is that the density always seems to be more or less the same, whether you have, and similar to these experiments with Bose-Einstein condensates, where you can see that the density is actually quite constant, irrespective of the size of the system. I think that's mostly due to the coupling strength of the vortices among each other.
Yeah, another one. It's a general question. We know that helium is the second most abundant element in the universe, and I'm just wondering. We know that neutral helium atoms are there, but in interstellar medium, do we get to see cluster formation? The cluster.
Yeah, good. I mean, in the interstellar medium, I don't think so, because I mean, you would need at least 3 body collisions, and these are probably extremely rare.
Maybe ions, neutral atoms and ions you may find, but
yes, sure. I mean, the acationic helium-2 molecule is strongly bound by 2.5 electron volts, so that's a stable, very stable molecule. I know that in some planetary atmospheres, or I think even on Titan, or a moon of one of the planets or so, it's expected that there's a lot of fluid helium. I think it's probably not super fluid, it's probably not cold enough, but yes, so on planetary atmospheres, there could be.
Yeah, thank you.
Very welcome.